Everyone, and welcome back. In the last chapter 10, we looked into sequences and time data basically, where we looked into how we process the sequence data, and we were just introduced to basic concepts and the techniques that go beyond. But first, we had been using some statistical methods. Then we went into some basic machine learning with deep neural networks. And I also explored how to tune the model's hyperparameters using Keras tuner, which was very efficient method indeed, because using the Keras tuner, we could actually get the values that were most optimum for our model. And so we didn't really have to do much of trick and trial for that, right? But this is something really different from what we have done originally. So originally in past, I think third or fourth chapter, we looked into convolutional neural networks, and we were basically using them uh, as a filter or to get the features out of images. And we've never thought or given a thought that convolution neural networks can actually be useful in sequence models as well. Indeed, they don't have images in sequence models, but we can still use convolutional neural networks here as well. So, like in chapter 3, I told you that we used convolutionals and we were introduced to 2D filters. Over time, the neural network learned which filter values were effective at matching the modifications made to the pixel to their labels, effectively extracting the features out of that image. The same techniques can be applied to numeric series, time series, but with the one modification, that is that this time we won't be using 2D filter. Instead, we'll be using a one-dimensional filter because we have just numeric data, right? So let's move ahead and see what we'll be learning. So a 1D convolution could operate on these as follows. So consider a convolution to be a 1 cross 3 filter with filter values of -1, 1 and minus 0.5, 1 and minus 0.5, right? That's the filter, right? So what happened in 2D convolution was we have some kind of kernel that was a filter, and we would pass all the values of the image from that filter, and we would extract the features from of that image using that filter. So now this minus 0.5, 1 and minus 0.5 is also that same kind of filter, and we'll be filtering out the values, the numeric values that we have through it, right? In this case, the first value in the sequence will be lost. The second value will be transformed from 8 to minus 1.5. So let's do some maths here. So the first three values of the numeric data that we have is 4, 8 and 15. And the filter is minus 0.5, 1 and minus 0.5. So we give 4 multiplied by minus 0.5 added to 8 multiplied by 1 and multiplied and added that to 15 multiplied by minus 0.5, and we just get the whole value together to get the value of minus 1.5. Here the value 4 was actually lost. That was the first value, right? So the filter will then stride across the values, calculating new ones as it goes. So for example, in next stride 15 will be transformed to 3. So the middle one would be transformed in each of the slots, right? Using this method, it's possible to extract the patterns between values and learn the filters that extract them successfully, in much the same way as convolutions do with images, right? In this instance, there are no labels, but the convolutions that minimize overall loss can be learned. So let's code some convolutions, and before that, we just adjust the windowed dataset generator that we used in the previous chapter with some changes, because when coding convolutional layers, we have to specify dimensionality. That's the core of using convolutions. And the window dataset is actually a single dimension, and it was not defined as a 1D tensor, and we always provide the convolutional layer with the tensor value, right? This simply requires adding a tf.expand dimensions statement to convert it into a 1D dimension tensor at the beginning of the window dataset function. So we just added this one. So window dataset, we just use series tf.expand dimensions. We pass in the series and axis is -1, right? Now that you have amended the dataset, so let's just add the convolutional layer. So we just defined the model dot keras model sequential. We added the convolutional 1D convolutional with 128 filters and kernel size of 3, and stride is 1 and padding is simple causal, right? Causal. Then we have 3 dense layers, and the last layer has just one output. The optimizer is SGD with learning rate of 1 into 10 to the power -5 and a momentum of 0.5, and loss is same, MSC, and optimizer is we have defined. Then we just fit the model. In the convolutional 1D, you have number of parameters. So filters is the number of filters that you want the layer to learn. It will generate it's this number and adjust them over the time to fit your data as it learns. The kernel size is just the size of the filter, right? So we had the filter of -0.51 and -0.5, so the kernel size would be 3. Strides is the step. So as we saw that we were taking one step ahead in the forward direction, the stride is 1. And then padding determines the behavior of the grid. So usually when we do padding is that we don't want to lose the data on the corners, because as we said that we lose the data in starting data, we don't really want to lose that. It might contain some information that is important to us, so while learning, so we really pad the surroundings so that when we are striding for one, or the filter is moving ahead, it won't lose that important value in the starting. So 3x1 filter will lose the first and last value of this because it cannot calculate prior value for the first or subsequent values for the last. So typically with sequence data, you will use causal here, and which will take only take the data from current and previous time step, never the future ones. So for example, 3x1 filter would take current step along with the previous two. Then activation function, we know we usually use ReLU means to effectively reject the negative values coming out of the layer. And the input shape, so we always have to define the input shape when passing in the data to the network, as this is the first step we have to specify it. Then training with this will give you a model as before, and you'll get the predictions. Given that the input layer has changed here, you'll need to modify the prediction code somewhat. So also, instead of predicting each value one by one based on the previous window, you can actually get a single prediction for entire series if you have correctly formatted the series in as a data set. So instead of predicting each value one by one based on previous window, you can actually get a single prediction for entire series if you have correctly formatted the series as a data set. So to simplify this, we have a helper function that we call forecast. So let's look. If you want to use model to predict the series, you simply pass the series in with a new axis to handle conv1ds instead needed for the layer with some extra axis. So you can do this using model forecast equals model underscore forecast, and then you pass in the series. And you can split the forecast into predictions for validation set using a predetermined split time as well, right? So let's see how we got the results plots. And here it is, convolutional neural network. We can see it's pretty good. It's coming in pretty good with the time sequence data prediction. So the question comes up that why choose parameters that we choose? Like why 128 filters? Why the filter size was 3x1? So the good news is that you can experiment with that using keras tuner that we already did, and we can explore something next as well. So there are some hyperparameters in with conv1d, and they we can usually, play along with those high, and we can change their values as well. So like in the build model one, we have the model architecture, and in the convolutional layer itself, we can set the minimum and the maximum value for all these hyperparameters like filters, kernel size, strides. So the stride might go from 1 to 3 with step of 1. Then the kernel size might go from minimum of 3 to maximum of 9 with a step like 3 steps. And the filter size might go from 128 to 256 with a step of 64. So we can play along with that and see what kind of results do we get, and rest all just remains the same. And for the tuner, we just have a lot of combinations of values here, and so experiment will take some time, of course. So we can try change other things as like small starting values and filters to see the impact, right? So we start small and then we go to the big with some steps given in it as well. Then if you ran the experiment 128 filters with size of 9, stride of 1, so it gave the best results. You can obviously see what results you get for the best. When you use tuner.search with the dataset and epochs of 100 and verbose of 2, you can surely see which of the, which hyperparameter value suits best and gives you the best results. Then we just add those values, just change those values and run it again to see if it's still the best. And after training with this, the model has improved accuracy, of course. So we used Keras tuner, and you can see it looks much better than the before one. So I have not experimented with this, but yes, the author says that there is a slight improvement over 4.47 MAE is, right? So we got without use of convolutional layers. Beyond the convolutional techniques, we can explore some other techniques like with Rnns, including LSTMs that are quite powerful when working with sequence data. And by their nature, Rnns are designed for maintaining context, so previous values can have the effect on the later ones. So that's why we actually used LSTMs, because they can actually have some context of the previous value with the preceding values and the upcoming values. So that's why LSTMs and Rnns are really important when we are dealing with some kind of numeric data. But we can still look into some synthetic data like NASA weather data. So it's actually a real data, not a synthetic one. You can create synthetic one, but this is a real data. It's quite a small data set, but not that big one, and you can get that on the official website as well. So it's a surface temperature analysis. You can just download a CSV file. It will look like something like this. So in 1950, the temperature was in Jan was this, Feb was this, March was this, and so on. And it's easy to process in Python. A CSV file, it's reading. You just open it, you read it in a reading format, and then you close it. So it's very easy to work with CSV file with Python extensions. And there are at least 12 data points of interest per line, so you'll have to consider it while reading the data. So I think you all know how to read data, a CSV file using Python. And if you don't, let's just go through it. So there's a function get data. So we define the file where we have to get the data file. We open the data file, we read it using f.read, and then we close it. So it's very important that you close the data file. And then we split it using the data with \n. And the starting ones, 0 ones, are the headers, and the rest are the lines. We have the temperature here, and then we split it and we add it or append it to the temperatures, right? Then we convert it into NP array, and the time ones, we arrange them with the length of temperatures, and we return the time in the series. That's what we require, right? And so if you are thinking that we have converted into a NumPy array, so it's because that once everything is complete, we have to convert it into a NumPy array called series, and another NumPy array called time will be created. That's the same size as the series, as it's created using np.arrange. The first element will be 1 and the second will be 2 and etc. and go on. So this function returns time in steps from 1 to the number of data points and series as the data for time, right? So they're correlated in a sort. Then we have the time in the series. We normalize that using mean and STD, and finally we split it as we require it in the test and training and validation. So we have the training time, training series, and the validation time and the validation series. We have window size of 24, batch size of 12, so shuffle buffer size of 48, and the same window data set as we were using earlier. And we just trained it. So the same one that we used earlier, window dataset function, we are using it as convolutional networks. We use convolutional networks and we trained on this dataset, right? So using Rnns for sequence modeling, now that you have the data from the NASA CSV in the window dataset, it's relatively easy to create a model. So we're just using a simple Rnn and 2 layers of that and final layer of a dense layer, and then we use it. So in this case, simple RNN layer is used. RNN are a class of neural networks that are powerful for exploring sequence models. So we won't be going into much detail about it, but RNN has an internal loop that iterates over time steps of a series while maintaining an internal state of time steps it has seen so far. So it would a simple RNN has an output of each time step fed into the next time step, right? So as earlier we get the same hyperparameter as before, or just use Keras tuner for that, right? So we use the same setting here, and yeah, these are the results of simple RNN. Though the peaks are a bit off when the pattern changes abruptly, but the whole thing is not bad, right? So wherever there is an abrupt change from high to low or low to high, there are some off limits, but yeah, still it's much better. So we can just use a Keras tuner for that. And also the validation and the loss is going good. Some kind of overlapping is there, but yeah, it's a healthy match between the training loss and the validation loss. But as the epochs increase, the model is certainly overfitting, right? So one reason could be that the data, being monthly weather data, is highly seasonal. So because there is seasonal, there are large variety of variations. And next we can see a larger data set, that is a Knmi climate explorer. So it has a more granular climate data from different locations of the world, and we can just use that data set to guess the daily temperature. I hope they do use this one. So just the same, you just read the file, open the file, read the file, close the file, as similar as the one we have done before. So it has around 90,663 data points in it before the training your model, so we have to split it appropriately. So we used 80,000 split time, and the rest we have left for the validation. And let's see, so it's quite a good, but I hope we just can zoom it a bit to understand much better. Yeah, so when we zoom it, we see that it's roughly the correct. It's not actually very accurate on this part. We would say the peaks, it's still missing on peaks. It's not, there is room for improvement. It's missing on the peaks, as we can see. So it's important to remember that we normalize the data. So while our loss and MA might look low, that's because they are based on loss and MAE of normalized values that have much lower variance than the original ones, right? So let's see, it's the next figure is showing loss of less than 0.1 that might lead into a false sense of security. So let's see how it's going. The loss is still high, the validation loss is still high, right? So denormalize the data, you can use the inverse method of normalization. So you multiply by standard deviation and add back the mean that we did earlier. We just subtracted the mean and we divided by standard deviation. So to denormalize it, just reverse the process. So if we want to use a different RNN, simply we used previously we were using simple RNNs, but now we want to use some different kinds of recurrent methods. So they are gated recurrent units and they are LSTMs. So you don't have to make any large changes. You just have to change simple RNN from both these layers and change it from to GRU or LSTMs as you wish, and then you can experiment with all these types and see that there is no one size fits for all solutions. So what works the best for your given situation, you just use that for prediction with the data, right? Next, you can use dropout layer. Of course, when there is overfitting, we always put so much stress on dropout layers for dropout normalization. So whenever you feel like there is some kind of overfitting, do try to use a dropout and do try to play with the percentage of dropout. Maybe it's 20%, maybe 30, maybe 40, but make sure that it balances out each and everything, right? So when using Rnns, there is also a recurrent dropout parameter that you can use. So what's the difference? Recall that when using Rnns, you typically have an input value and the neuron calculates the output value and a value that gets passed to the next step, right? So the dropout will randomly drop out the input values. Recurrent dropout will randomly drop out the recurrent values that get passed to the next step. So what's the difference between normal dropout and a recurrent dropout is that why we use recurrent is that it gives you the output value to the next step and even passes the next value as well, a value that gets passed to the next step, right? It calculates the output value and a value that gets passed to the next step. So the normal dropout would randomly drop the input values, but the recurrent dropout which actually drop the values that is getting passed to the next step, right? So there that neuron won't be learning the value that was coming in. Here you can see the inputs to the layers at different time steps x. The current time is t and the steps shown are t minus 2 through t plus 1. So t minus 2 till t plus 1 the time steps are given. The relevant output at the same time steps y are also shown. So what are the outputs at y are also shown, right? The recurrent values passed between time steps are indicated by dotted lines and labeled as r. So what values are passed to the next neuron are also shown in the dotted lines. So using dropout will randomly drop out the x inputs. Using recurrent dropout will randomly drop out r recurrent values, right? So this is the kind of difference between normal dropout and the recurrent dropout. So here is some citation as well for a paper from a theoretically grounded application of dropout and recurrent neural networks. So if you have some interest into going deeper into dropouts, to have a look at these. And there's also some more work discussed by Gal in his research around uncertainty in deep learning, where he demonstrates that the same pattern of dropout units should be applied at every time step, that a similar constant dropout mask should be applied at every step. So while dropout is typically random, Gal's work was built into Keras. So when using tf.keras, consistency recommended by his research is maintained. Right. So how we use dropout? Just use it in the layers. So dropout equals 0.1 and recurrent dropout is 0.1 as well. So just train using that. Each parameter takes a value between 0 and 1, indicating the proportion of values to dropout. The value would be 0.1, means it's 10% of the requisite values. So that's for that. And yes, you can see some hinges over there while training. You can see that the loss in Knmi decreased rapidly until about epoch of 300, after which they continue to decline, but quite noisily, right? There you often see noise like this in loss when using dropout. So whenever you see such noise in the loss, it's because we are using dropout. and it's an indication that you may want to tweak the amount of dropout as well as parameters of loss functions such as learning rate. So you might want to change a bit of the parameters here and there, so it won't come in such a noisy manner. Predictions with this network were shaped quite nicely, but there's room for improvement. Of course, the peak predictions are much lower than the real peaks. So you see, we are still not able to reach the heights of the peaks. So there is still some tweaking left in those hyperparameters. But then we can use an additional technique using when classifying sequences is use of bidirectional training. So we have heard about it, we have read about the bidirectional training. So it may seem counterintuitive at first, as you might wonder how future values could impact the past ones. But let's recall that time series values can contain seasonality, where the value repeats over itself. So some kind of past data has some connection with the future data, given that the data repeats a signal for how data can repeat might be found in future values. So when using bidirectional training, we can train the network to try to spot patterns going from t to time t plus x, as well as going from time t plus x to time t, right? Bidirectional. So what we do for directional is, the coding is very simple. Consider GRU for previous section. To make this bidirectional, you just wrap it around GRU layer around tf.keras.layers bidirectional. You just call that. You just have to wrap it around that. So it was again going in one direction. Now it will be going in both the directions, right? And similarly for the second layer as well. So let's see how GRU worked with the dropout as well. So this network has a MAE of about 0.4, chiefly because it doesn't seem to do too well with high peaks. Retraining it with larger window and bidirectionality produces better results. So MAE was about 0.28. So here, now you can see that larger the window and bidirectional GRU results, it is richer for much higher heights, right? You can clearly see some difference here. Ideal choices are very much dependent on data. So skills you've learned in the chapter will help you with the specific data sets. So here we are for the summary of this chapter, that we have explored number of networks, types of building models to predict time series. We have looked into adding convolutions to time series data and playing with it. We have looked into Rnns, LSTMs, GRUs. We have tweaked the hyperparameters. We have used Keras tuner for that. We have improved the model accuracy with practical real-world examples and data sets. And now we are ready to start building networks for a variety of data sets and a good understanding of what you need for, to optimize them. In the next chapter or in the next part of this book, we'll be knowing how to use these models. So till now, we have just trained these models, we have tweaked the hyperparameters, we have got our accuracy, we have looked into the graphs for losses and accuracy, and now it's time to actually put them into some good use and see how we can solve some real life problems using these models on our web pages, on our mobiles, in apps, and iOS, Android, and whatnot. We can use them into maybe into the simple processors like Arduino or Raspberry Pi, right? So let's just go ahead and work these things out. And now we'll just jump into Google Colab to have a look at the code for this previous chapter that we have recently completed. So let's jump off. So let's jump to code section for chapter 11. So we have already seen this code and we have some idea of how this code looks like and what were the plots and the projections. So we'll have just a quick look, and first we'll be installing Keras tuner. So just simply, use pip install Keras tuner if you don't have it installed. Then for the imports, we have TensorFlow, NumPy, Matplotlib, and Keras tuner, of course, and we have to import random search for that. Then this code, I hope you're familiar with it. These are some random plot functions, some trend and season patterns, seasonality, and some noise functions, and splits that we have already done, the random plot. And then we have a window dataset function, we have a build model where we just add the layers to in the sequential. And finally we have the tuner. We tune it. We tried to have a trial of 24 different hyperparameter variations, and then we got the best loss was around 59, right? So it took around 39 minutes and 6 seconds for that. And finally TensorFlow automatically triggered it into an exit. It took a lot of time. Then we have the model again for optimizing the results that we got earlier. So it was like we got good results when we were using 128 filters, the kernel size was 9, the stride was 1. So we used it as we have already seen in the book itself. So you can see the loss was pretty high in starting, and then it went down to 60% and somewhat around 60-61% till the end, right? So you can see the plot here, the final plot. It's a bit off, I would say. It's not a really good one. The metrics mean absolute error was like 5.05, which is really not that good that we expected. But yeah, surely we'll try to change and tweak the hyperparameters here and there to get the much better values. Then we played with the NASA dataset. Weather dataset, we downloaded it, then we opened, read it, then just split it into series and time. And finally, here are the plots. So for the window dataset and the model using simple RNN, and the validation accuracy, the validation MAE was 0.22, while the training MAE was 0.20. So it's nearly similar, right? So here's the forecast. You can see, as in the book itself, we have seen that the validation and the loss of accuracy were pretty near. So the peaks, the output is reaching to the peaks. Yeah, it's not overfitting much. So you can see the MAE went down to 0.24. So that's a brilliant jump from 5 point something to 0.24. It's a brilliant jump, right? So yeah, this is the wrong one, so don't have a look at that. And yeah, Knmi Climate Explorer dataset, similar to the previous NASA one, right? So we can see, yeah, similar kind of things. 0.29 MAE for the training, and validation is 0.26 and 0.27. So it's kind of the same, right? This is the zoomed out version. So there is no much of the change that you will see from that will be different from the book, right? So do give it a try. The code will be in the description. The link would be in this description. The code is hosted on GitHub. So you just open up to the Colab and just work it out. You just have to run it one time, right? And yeah, replacing Rnns with GUs, and we have actually read this about just layering it with bidirectional, so wrapping it up in the bidirectional one and getting the outputs, right? So GRUs are replaced by LSTMs. What happens then? It was a very bad fit, actually very bad fit. So yes, so that's it for the code. I hope you enjoyed this series and you are certainly excited for the next one, where we go to the other half of the book and we look how we can actually implement those models that we have trained with our own hands. And the code would be in the GitHub and the link would be in the description. Do check out the code, and if you have any doubts, do leave us a line in the comments or just reach out to us on our Twitter handle. And till then, keep learning.